when you have a major fault. Like, so for example, there's lightning strike, hits a tree, brings down the pole. If you are in a rural area in France, because obviously you have better infrastructure than the US, here is full of poles everywhere you go. But you could also have a line tripping and so on. So in summary, right, all of these type of perturbations or they produce disturbance forces. And you have across the entire power grid in Europe, many electrical machines, synchronous generators, and also other types of devices that what they need to do is to develop restorative forces, okay, that are greater than the disturbance forces to try to come back to some sort of quasi-equilibrium. So in the case of conventional power generation like nuclear plants, these synchronous machines have to stay in sync, basically, with each other, rotating over 50 hertz in sync. And they have to overcome these forces. And if that happens, the system is stable. If not, if that doesn't happen, you start losing synchronism. And the loss of synchronism is really what makes a system unstable. You can have that locally, so one generator can go unstable with the rest of the grid, or one power plant, or you can have this as a phenomenon that many groups of power generation, start going together, losing synchronism with the rest of the system. And those are typical different types of dynamics that we observe. So you have all this, I'm talking mostly about conventional generation, but it's the same thing if you have wind or PV generation. They still have to be synchronous. They still have to produce an output that is 50 hertz. But now they will have many control loops inside of them, and they need to function properly. And they need to function properly across many circumstances as the system changes. But what happens is that might not always be the case. There could be a system change that, as you saw in the first slide, you can start going unstable. So basically what we want to be able to do is to monitor this degree of stability for the dynamics of the systems, and something, to monitor something, we need to do it quantitatively, right? So in general, when you study these problems, here you have a power plant inside. This comes from a library of modeling for power grids called OpenIPSL that is developed by me and my team. And it's equation based, so you can go and run simulations on linearize and so on. So here you have the power grid and you have a power plant connected to it. And you have two cases. Example one, you see how it goes unstable, right? And example two, you can see it goes stable. So that's the difference between them is in one of them, I have added a controller that is well tuned to dampen this response when you have a large disturbance applied to the system. So that's one example, right? So what is the difficulty with this approach of doing simulation is that you don't know how stable or unstable the system is just by looking at the time series. You could say, yeah, well, it's going unstable, or yeah, it's going stable, but you cannot say, how much. And so what we use for that is damping. So that's how we characterize this what we call electromechanical dynamics, basically. I think as the system operates, it will go from set point to set point, and it has to adjust to these different kind of perturbations that you will see. Perturbations such as the load increasing, right? The consumption, more customers turning on. You can think about the morning when people starts getting up and starts turning on stuff. So the system has to increase dispatch as more demand goes. And to be able to adjust to that, you have to have what we call small signal stability, just able to do tracking by all the power plants in orchestration within the system. Okay, so uh, how can we quantify the stability of the system? Well, you guys are very familiar with this. Is basically we can look at linearizing the model around an equilibrium. So you have your set of equations f of x. You want to linearize them around a neighborhood. You have your A matrix, and we know how that response behaves. So this boils down to calculated eigenvalues if you have a linear model. So here we take the we solve the for the eigenvalues and the eigenvectors, and you can calculate from the eigenvalues the frequency, and from the eigenvalues you can calculate the damping for each of the modes. So the damping is important because we will use that, as I started in the first slide, as the metric telling us how stable or unstable you are for each of the modes that you see. There's more than one that you have in the system. You have many, many. So in this example that you see here, you can clearly see one, but there's another guy over there if you look at the curve here. So from the same two examples, here you can see the dominant mode in this example is the interconnection of the power plant with the rest of the grid. That's what I have modeled. So as you see here, in this case, in the blue case, the power plant loses synchronism. So the speed goes, instead of staying at one will mean that it's synchronous with the remainder of the grid. After the disturbance is gone, after you apply the disturbance, this one grows and loses synchronism, while the other one keeps it. And now we can see it very clearly here that the reason of losing synchronism is because you have basically a pole on the right-hand side, an eigenvalue that has a frequency of 1.28 with a negative damping. And by adding a control system and well calibrating it, we can mitigate that to 20 and have a damping of 24%, so you can move it to the other side. So obviously, you can use these techniques to monitor changes in the system. We could have change in the structure. So removing one of these transmission lines, that's changing the structure. Here I changed the structure because I added a controller, but the techniques are general and you can apply it. But, and here is where system identification comes in, you don't have these models. So here is a more complicated example. This comes from this little paper here, and just so happens I am giving this same presentation in Ecuador next week. So I have prepared all these examples with information from there to motivate the talk. So it's nice that I had the same. So the mode that I was showing you at the beginning of the slides and the behavior that I presented you in the example is exactly the same. So you see here, well, not exactly the same phenomena. So you see here at the beginning, damping, the damping is deteriorating. So you have growing signal, and the eigenvalue is on the right. So this is the same case right here. So that's this local mode that is with the largest hydropower plant in this part of Ecuador. And Quito is over here, if I remember correctly, right there, here. So now there are other dynamics in the system. So we only analyze one that is product of what we call a local mode in our power system parlance. That is one group of plants. So in this power plant, you not only have one generator, you have 10, 20, whatever, but we model it as an approximate one, but it's interacting with the remainder of the grid locally, which means that it's not spreading throughout the network, or it's not spreading through large regions in the network. So those are different types of dynamics. One is that you could have interactions within the power plant itself. you can start having generators firing at each other. The local one is the one that I've been showing you, and the next one is the one that we will cover in the rest of the presentation. That is the inter-area one, where you have a power plant, let's say here in the north, and is going to interact with through the network with the power plant in the south. So it could go through here. These are high voltage transmission lines in yellow, 230 kilovolts. So you could have these two paths, and that is another dynamic. So it gets more complicated, kind of the point being. And all of these values that I'm showing here, they have calculated it in this paper through statistical analysis of the identification problem. So how do you get measurements? Just to give you a little bit background, you have in a power substation two transformers. One is for the voltage, one is for the current. And this will go into this device called phasor measurement unit. So that's how they're gathering locally. Now you have, as in this example of Ecuador, you have hundreds, if not thousands of kilometers dividing between this power plant here in the south and this one in the north that interact through the lines. So you have to have synchronization in the measurements to be able to compare them across a wide geographical scale. So for that, you have a GPS signal inside of this PMU device, and then that is time synchronized using GPS disciplining. The data then is streamed out over TCP/IP protocols usually, or UDP, and there is a standard for that. I could give you a talk just to that because I wasted my life building this thing. So anyway, and to be able to aggregate many of these PMUs, you send them to something called a PDC, a phasor data concentrator, where you can build software applications that allow you to do the monitoring of the frequency and the damping, which is oscillation monitoring software. And in the case of Ecuador, they have this software called WAP Protector that is acquiring all the data coming from all these different sensors. And inside of it, they do all the data pipelining, and they have one of the applications is this of oscillation monitoring, where I started the discussion. So effectively, the problem was that they were installing a power system stabilizer, something that we are playing around with Javier a lot, but the control parameters were not set correctly. So when they commissioned the plant where they connected it to the grid, it started oscillating. Now the problem is that this is it's a very large power plant, especially for that system. So having the plant starting to oscillate can create a lot of problems. So they had to turn it off, redesign or retune the stabilizers to be able to operate the plant. Of course, this design that they have is based on power engineering rules and following very old design techniques like root locus and lead-like design. Usually, that's what we use. Okay, so you can see that this is actually has a practical purpose to do identification of frequency and damping from the signals around a power network. It's useful, and there are real-world problems that need to be addressed. So I showed you examples doing simulation models, and in fact, you can do much more analysis with simulation model that you can do with measurements, but in the power system field is very, very hard to maintain. In fact, it wasn't until a couple of years that there was a whole European interconnection grid model yet available for studying dynamics. And the quality is low, and it's not updated all the time. So the only way to go is to use models from measurements. And I like to explain this, that, these types of models are just like a transfer function, can be identified from data under both normal operating conditions, what I will call ambient data, and during large disturbance, that I will call transient data. I don't know. I think I'm doing good with time, right, Xavier?
Yeah.
Half an
You're
hour left, right?
for 20 minutes, let's say. So yes.
Okay. Okay, I took a little bit too much time at the beginning, but I think that was important for you because the rest is going to be a little bit obvious for CID people. So you have large students, and you have this, we call it transient data. And then what it becomes interesting is that there are few stage tests or experiments where you actually inject probing signals. And these models are, even though they're limited by the bandwidth of the measurements and whether or not you have a probing signal, they can give a useful representation for the monitoring problem, which is critical grid dynamics, different of the mode frequencies and dampings, for both monitoring and control design. And we can do this even better thanks to SysID by specifying constraints on the accuracy and the precision of the estimated parameters. And that is via specifying what's it called? Variance bounds. So you know the basics of this is, here's another example. This was in 1996, and that was a big event where they started having some of these PMU measurements, but there was very few. But this event really was the one that got the utilities in the U.S. and the Department of Energy to put money into the real-time monitoring, because when they tried to reproduce this behavior with the model, they were incapable of it. So they realized that you can't just live with simulation models, even if they're pretty good. You have to use some sort of monitoring. So that's kind of we're trying to track dynamics over time. So if you look at the beginning of the time series and you do a blind estimation, or I forgot the correct name that Javier has taught me, but
Time series.
output only estimation, I think it's called. If you do it with this chunk of data here, you will get a result of damping. But as you move, your damping is going to degrade. It's going to become lower and lower, even to negative. And you have time there to apply remedial actions or even preventive actions or corrective actions. So what we're going to do is that we're going to try to approximate the model to this discrete time representation. And basically, A of C theta will contain the characteristic equation. When I was young, they taught me that. But anyway, in the C domain, you have the poles of the system, and because that's in discrete time, you have to convert it to continuous time. So that's an additional step you have to take. So that you can extract the eigenvalues. So from the eigenvalues, as we discussed previously, you can get the damping and the frequency for all of the modes that you could observe in that set. Okay. Right. So this is the way that we see it, or in the power community, the few people that work on this, that you have variation of loads that is randomness. We represent that as integral of white noise. So this is going to be applied to the system G, and you're going to get some sort of response that looks like that from that signal. If you get like a big transient, you're going to get a response like this. And if you have a design signal, a probing signal, you're going to get something like this. Well, as you know better than me, everything is combined in a single signal. And the reality is that you don't have this many transients. So really, to do continuous monitoring, you're dependent in your ability to get good estimates on their output only, or on their close or with probing input. So to do to obtain measurements, you can, as I said, wait for something to happen. But there are some experiments, very few of them. This is called a toaster. This is to make system scale experiments. So basically, this is a big resistor that they connect to ground. You can only connect it for about 3 seconds before it kind of consumes itself, it blows off. And that allows you to create a transient in the system. So here you're increasing about 150 megawatts of load. That's a tremendous amount of load uh, uh, to do an experiment. But of course, we know that this is a very nice signal to do identification on, and you can calculate a very nice model. So in the western part of the U.S., in the model that I was showing you, well, no, in the system here, they have an inter-area dynamics that goes from the north to the south, and that's the one that they're trying to characterize here. So they have a very nice fit from these experiments. Now, yeah, I was one of those, but this is kind of very intrusive testing, right? So if you want to do the continuous monitoring in the US, they have these tools. So now I tell you this example because here you can see what we call a mode meter. So you have here the California ISO, the old, this picture is a little old because you still have a light board. But here you have the computer, and inside of the computer, you have what we call a mode meter. So it's like a speed meter, but it's for each mode, you have the damping on green, if you're in good shape, yellow, and red. So the idea is that as you progress through the time and the damping is changing, this will move around, okay? And if you get yellow, you gotta do something about it. And here at the bottom of the screen, you can see the two modes that are being tracked. The distance to the damping line is easy to just eyeball it on the x-axis. That's why they do like this. But what is important in this picture that I didn't have in the other one is that you can see the past estimates, right? So as the system is moving, you have past estimates. So the question now, and this is really the interesting part for you, is what is a good mode meter estimate? Well, you could have lower variance, you have a better estimate, larger variance, you have a worse estimate. That this is really where system identification can help us together with input signal design. For input signal design, this is the same network in the Western US where you have this high voltage direct current light, HVDC, where you can inject this modulated signal or this probing signal to do the input-output characterization. So these experiments do exist. They are rare. They do it every other year, I think, but it's something that is being applied to characterize this part of the American network. Okay, so now to more researchy things. The state of the art on designing these experiments is basically shown in this report from 2021, and it's a plus minus 20 megawatt signal that you can see here. Now the signal has been designed in such way that you see here the magnitude of on the x-axis is the frequency of the sinusoid that you're going to inject. And you can see here how they basically reduce it as you increase from 1 hertz. So they have maximum peak-to-peak energy that they can adjust, and they adjust the phase per sinusoid. And then they limit the content to of the signal they're going to apply from 0.1 to 1 hertz. And they apply it for 10 to 20 minutes, as you saw here before. So this was 20 minutes that they're injecting the signal. So these people have been doing this since the 90s. So they have a good idea of what the system looks like, what the dynamics are. So the question is, how do you design these signals for systems with lesser known or even unknown dynamic and changing dynamics? The other research questions that we try to do is that can we reduce the controller's effort by minimizing the input signal spectral power, or to limit the impact of the system, which is the most important sort of point of view from the operator, power grid operator, by minimizing the output signal spectral power, while maintaining the same, maintaining high accuracy and precision in the estimated parameters. So that's the big research question that we did. And the last one is really how can you test the design signals before you apply them in the field. So I'm not going to spend too much time of this because you guys are the experts, but basically what we're going to try to do is that we're going to inject a probing signal, and in the simulation case, that is what we are going to show you. We also create this random perturbations, so we can characterize G of Z and H of Z and obtain measurements. And through system identification, what we're going to try to do then is to get an estimate G hat and H hat that we can use for enhanced grid dynamic monitoring, which is what we will talk today, by calculating the frequency and damping of each of the modes. And in the experiment design part, we're going to design the constraints to increase the accuracy and precision of those parameter estimates. We could also do enhanced damping control. That's what we're working with Xavier the last summer and this year too. Hopefully, we'll try to present something some other time if you're interested. So what the technique that we will use is the prediction error method, which I assume many of you are familiar with. So basically what we want to do is to find this parameter vector theta 0 by minimizing this error, which is the prediction error over here, E theta, ET theta over here. So this is the prediction error that we're trying to minimize. So of course, the larger the number of points over time, the better the precision. But since we want to replicate what is being done in the real world, we will try to build these estimates every 5 to 20 minutes because that's kind of how they're applying it in the field. And I don't know if I missed anything that is important here, but if not, Xavier will correct me. Yes, sir. All right, so what did we do that is new? So if you see theta, it's really just the coefficients of the transfer functions that we're going to use. That is not frequency and damping. So one of the things that one of our collaborators did was to take these transfer functions, and instead of defining the parameter vector theta in terms of the coefficients of the transfer function, in the case of the denominator A0, you have theta A. We represented this instead in terms of the damping and the frequency directly. And what that allows us is to avoid to do the Turing transformation, but also it gives us a direct relationship of the between the damping. Well, we treat damping and frequency as parameters that are needed to be estimated directly from the model structure. Now, to do it, you need to do the parameterization. You have to compute, instead of G hat Z theta, you have to do G hat Z. I forgot this, beta, I think it's called, which is, or is it correct, sir? Beta?
Rho.
What is it? Tell me, because I don't remember the symbol.
Rho. I put it in.
Let's see if it does. Ah, rho. Okay. Thank you. Rho. So we have to estimate rho instead. And this, you need to do all of these symbolic analytical expressions. So that I'm not going to show you, but that's one of the things that we did that is useful, actually, from my perspective. Okay, the next step. The next step was the optimal probing signal design. So here we have our model structure. Now we're going to decide our input signal. We have this multi-sign where we have the magnitude of the signal and the frequency and the phase. Now, the power spectrum of the multi-sign is given by this expression. So basically, this the optimally styled problem is gonna boil down to minimizing the spectrum of the input signal and the output signal by weighting how much impact each of them we want to reduce, and that we're going to do through optimization. So in this optimization problem, we formulated in such way where here theta u is the power spectrum of the input and theta y is the power spectrum of the output, and we put this coefficient 1 and constant 1 and constant 2, which are our weighting factors, so that we can target either the power spectrum of the input or the power spectrum of the what's it called? The output. So that is the trade-off that we have to study, and this basically is the methodology developed by Xavier and his gang that we're going to apply. So basically, in these two little examples here, we have a conventional multi-sign where you have all the spectrum excited versus the proposed method that will only excite certain frequencies. Okay, so that gives us some ability to excite the system in a way that we don't have to do the whole spectrum, basically. So in the following experiments that we will do, what we're going to do is that we're going to apply a base input signal. The base input signal is going to be used to estimate a base system estimate G and an H. And that will allow us to calculate the variance also. So once we have done this base procedure, we can have a reference, basically. And then we will do two new experiments, one with a signal theta u that is exactly the same as the first signal that we applied, and one with the design optimal input signal. And why do we do this? Because this will allow us to use the result from theta u1 of t. When we apply this signal, we can then calculate what is the variance that we get with a dumb signal. And that variance, when we apply the optimal signal, will be used as a constraint. So here, basically, we're figuring out, if you apply this dumb signal, you're going to get this variance. Therefore, our optimal signal has to have better variance than that. And that's what we call a user-defined variance, but we do have this approach to calculate. Okay, so here is a simple example. Here is the similar power system that we showed at the beginning. And here you have points where you can inject different type of signal, okay? The idea here is that we will inject U of t over here and measure Y of t over there. This could be done with some equipment called like a static bar compensator or there are some devices that only inject reactive power. Now, the next thing that we're going to do is that we are going to set 0 in the optimization problem in the second part. So effectively, we will only solve for the energy of the probing signal, and we're not going to pay any attention to the output. Okay, so yes, and so here you see the dumb signal U1, and now here you see the optimal signal U optimal. What we have is that the mode is 1 hertz, and that we got as estimated, and the true one is 1.1. So we do have a bit of bias, and the damping is 7.9 instead of being uh, 8.2. We have a 96.5 fit. So it's a pretty good estimate, because if you look, we only have 2 minutes of data. Okay, so this is example is more to show that even with reduced amount of data, you can get an acceptable result compared to what we are using in the field today, in the real world. So, and of course, the spectrum shows you here the dumb signal having the full spectrum, and here the signal only having certain frequencies excited. The main dynamic is at 1 hertz, so you can see that it's injecting frequencies around here only. So, okay, here in the second example, it's really what matters from the point of the grid operators is that they are concerned of doing this kind of experiments, at least all the people that I talk to, because, oh, you know, we don't want to shake the ball. We don't, you know, don't inject, don't give us more problems. So the idea is to show them, like, well, you can apply this technique and this and put a high weight on the impact that minimizing the impact on the system. So in the same modes, we have a good fit. But now, if you look at the optimal signal that we obtain, is has 40% lower power than in the previous case. So we are indeed minimizing the system impact. And I don't remember if there's anything else I should mention here, but yeah. Okay, so I have one more example where basically we deal with this inter-area mode that we talked. So I'm trying to mimic, we're trying to mimic what we saw in the real world, that there is this HVDC interconnection connecting in parallel to the AC system. And we're going to modulate the input signal here. And here you have the measurement, and you have a frequency of 0.63 hertz and a damping of 1.5. So that's pretty bad. So here we apply 0 on the output, and here we apply a high weight on the output. And in the input, we apply a 1 here, and here we reduce the coefficient. So effectively, you can see the main dynamic of the inter-area mode is right here with the dashed line. And you have a couple of frequency injections here, but you also have some there. This is another area, the local dynamics of the other machine. So there is a local dynamic that is going in like this between G1 and G2, another one that goes like this, and then the inter-area dynamic is these guys against these guys like that. So when you don't apply any constraint on the impact of the output, of course, you're going to naturally have well, even without even when you put the constraints, these dynamics are getting excited anyway. So and here you can see the example where we try to mitigate the impact on the system while also allowing a little bit more of impact on the input signal. So we allow more energy in the input signal. So you can see the scale here is almost double in this case for these two poles here that are the frequencies that you need to inject. Okay, so but in the time domain is really the interesting thing, and this is what people in the industry will look like, that instead of injecting a signal that looks like this, it's really the input signal looks much smaller. So that is a concern for the equipment where you're injecting the signal, and then on the system, well, in terms of amplitude, you don't see a major difference on the amplitude between the signals. So that will satisfy both the variance. Sorry, that will satisfy the need of designing of applying an input signal is not dangerous. Basically, is what I'm trying to say. Now the question is whether or not we're going to get more accurate results. So here you have some bold plots because we're using these nice modeling tools that I've been developing for more than 10 years. We can actually have the true transfer function of the system from a linearized model. So that's the blue line that you see here in the bottom. And then you have the base experiment is in purple, and G of one is the DOM, and the op2 is the optimal input signal. So you can see very well that we can characterize very good this inter-area mode here of the peak, but we do not capture at all the other two local modes, right? Because those are first of all, the model structure that we have picked has only 4 poles, while the system has 46. So of course we can fit very well to this inter-area dynamic, but we cannot capture the other ones. But that was not our goal. You know, if that was our goal, we will have to modify the model structure and target those local modes too, which might not even be possible depending on where you are injecting the input signal. And then doing 100 Monte Carlo time domain simulations on the model, applying the signals, we get the variance of the base procedure. It's 4.610 to the -7. Then we have the what's it called? The first the dumb the optimal signal 1 and optimal signal 2. So here you see that we have reduced the variance, which is what we wanted. We do have a little bit of bias. Now, if you look at the normalized probing signal power, of course, the base procedure is 1 because we're it's just the DOM signal. But in the other 2 cases, where we are having the coefficient 1 and 2 being set, the probing signal and the measurement signal powers are reduced with respect of just a normal sinusoid. And in the paper that I cited before, we have an even larger power system model. Xavier is probably now very aware that in the comment that you get from reviewers is always asking you to apply it to a larger power network. You get that comment for free. So there's another example there. I have plenty more slides, Xavier, but I don't know if it's advisable at this point to continue. I think maybe we should stop now because I think it's right on time. So maybe I should just go to my conclusions and
yeah, indeed.
Yeah. All right. So what the main goal of all this work is to tell people that probing signals can be really designed so that we can give some sort of confidence that the power spectrum is going to minimize the disturbance that we apply on the system, while giving you better accuracy than just doing it this output-only identification, basically. You can address specific needs from the application in this case by reparameterizing the models. It does need some work. It might not even be necessary in practice, but this is what we did. You know, from the research perspective, it's neat, but you know, I'm not sure you actually need to do this in practice. Just apply the testing transformation might be enough. And from the point of view of application, this really has a very good advantage using this technique, because you can give some guarantee that whatever input signal you're going to apply is not going to damage the equipment that you're going to, the actuator that you're going to use for probing, and that you're not going to disturb the system more than what, well, more than what you need to do good identification. We could extend this method to optimize for the random phase changes. But really, the other part that I didn't cover, because I kind of still waking up by going very slowly, is that there needs to be some sort of proof of concept in lab scale to convince some more of the utilities that, you know, the one that I show you is the only one that I know in the world that does it in the western of the US. So it's going to be tricky to convince people to do experiments, but I think this is kind of my goal with working with Xavier, that we can show them, at least in paper and maybe in my lab, that it is possible to apply these techniques and take advantage of them. And we're doing that. We're having a collaboration that we are applying this prediction error methods, and we're trying to now do the monitoring, but also do the control redesign exactly for one of the PSSs as the real world example. So I wanted to bring that example today for Xavier too, because it's the problem that we've been working for a couple of years together. Anyway, here is some of the rep. I will send the slides to Xavier after we finish. Here's some of the papers of the probing design. This is of the prototyping that I didn't show you, and here is the one for Ecuador. And thank you very much for inviting me. So now we have time for some questions, right, Xavier?
Yeah, indeed. Thank you, Luigi. So questions from from the audience here in the room or on Zoom.
May I?
Yeah, go.
Yeah. So thank you, Luigi. Very nice presentation. Let me just activate my camera. Okay. I have a couple of questions. First one, you started with the kind of box-jinking models, and then you switched to an RMAX model. Is it just a simplification of the first model, or?
Yeah, I'm sorry for the sloppiness. We used at the beginning, I was just using the two kind of here. I think this is what you mean. This is, I was just using to motivate this example. Now, what we used in the technique, it was all RMAX models. So.
And what motivates to have the same denominator in the model, in the noise model as in system model?
Well, this is the chicken and egg problem that I think that Xavier talks about a lot. The motivation is that we are assuming that the dynamics that we're exciting from the random loads are exactly the same, and then you have this characteristic that this is the error that you're trying to minimize, right? So if the poles are correct and your estimates are true, are close to the real system, then this error could be zero. So those are how I would respond. But I think Xavier could be better fit to answer this question, actually.
Well, just for the RMAX, of course, all the pole system, the poles are fixed, and of course, where you will measure, you will excite at different location, you will measure at different location, and so normally the transfer function between any points will contains these poles. In fact, it's a big closed loop. It's and so when you excite a closed loop from one point to the other, well, any closed loop transfer function contains same poles. Of course, in a network, you don't see all the poles so well Yeah, there's some unobservable poles in 1D. But basically, if your excitation and the random load that you see next to the random load that are observable at the point where you measure, and if your excitation and the measure points are not too far away, well then of course the dynamics will be the same in the excitation model and in the random load models, because it's two excitation. One is unknown and the other is what you excite. So, but effectively, it's true. Armax model works quite well. But Book-Jenkins at the end is sort of also, in some cases, Book-Jenkins gives better results. So, so that's sort of
much more parameters.
Yeah, indeed. So there are some difference, and sometimes effectively it works better. So, but effectively, it's because
we've used both in other, not in this results that I showed, but we use Book-Jenkins in other work that we're doing. So it's a bit testing which model works better. Sometimes you have to do that.
Okay, thank you. I had another question actually.
Yeah, sorry. Go ahead.
No, I forgot my other question. Yeah.
We got the question?
It came back. So you were computing the input signal, but I mean, no, you were computing the best input signal, but I didn't see how. Yeah.
Okay. Yeah, I didn't explain this in detail. So how do you solve this problem? Is basically you're going to apply or select C1 and C2, and then you're going to solve this minimization problem. So theta U here is going to be the spectrum of the input signal, and theta Y here is the spectrum of the output signal. The first term C1 minimizes the effort of the actuator, and the term C2 helps to minimize the impact of the output. So you have to run this optimization problem several times with different coefficients when you're designing the input signal, basically, to find the best trade-off.
Are C1 and C2 two scalars?
Yes, they are.
So you have
a weight. You have a scalar weight. Yes. Okay.
So you have a predefined power spectral density. You have two predefined power spectral densities, Phi and Phi, and just compute two parameters, C1 and C2, right?
No. You select C1 and C2. You say, I wanna put more importance on minimizing the disturbance. That will be C2.
Okay.
Okay. So then you set C2 to 100. Then you're going to solve the optimization problem, and the optimization problem is that you have to find this ARs, which is the amplitude at each of the frequencies that you want to probe. Okay. So what we have preset on is theta U, the signal type, the type of the signal. We have pre-selected it as this equation, and then we have created a grid of values of frequencies. Okay, so 0.0, 0.001, 0.002, etc. So now the optimization problem, if you put C2 equal to 0, then the problem is only going to find these coefficients AR. Okay, it's going to find those by the optimization, only considering the spectrum of the input. When you add the spectrum of the output, then it's going to find those inputs considering both of them.
Okay, fine. And what kind of optimization algorithms are you using?
In this result, the tool that, well, the algorithms that were used were, in the past it was Gurobi. Then from Gurobi, we moved, I think, to something that didn't cost money. I think it was, I have to check what Schur used.
Is it
But
kind of LMI that you are solving, or is it a gradient-based algorithm or something else?
It's a convex problem that can be solved with LMI.
Okay. Thank you.
But in the recent time, we have been using some Bayesian optimization that Javier likes to use.
Yeah, but that was
So,
kind of controller, not
Yeah.
to the expert.
but you could use it for this too, the optimizer, right? Or not?
Yeah, but well, yeah, of course, you could also, yeah, you could also use fmin-con here also, but that's not necessarily convex. So.
fmin-con was not doing very well. I think that's one of the guys that worked on this, indeed, the one my PhD student, he used Gurobi for a while because it's very efficient. But I mean, right now there's so many good tools that I think probably any of them could do well. Anyway, but this whole method is what Xavier developed in if you like the math and the details, those are in that paper. It's all Xavier's theory, right? So I barely understand enough to apply it and be dangerous. Anybody else?
Other questions? Well, I guess everybody is starting to get a little bit tired. So Luigi, well, I would like to thank you once again for having done this presentation. And so let's thank Luigi once again.
Thank you. It's my pleasure. I hope I can join you in person sometime. I enjoy very much going to.
Well, next time you will be in France, we'll arrange something so that you are in person. It's
Yeah, my pleasure. Thank you, everybody. I'm going to apologize to leave, but I need to go to the Thanksgiving celebration, so I have to drive a few hours.
Okay. Have a nice Thanksgiving and be nice
Thank
to
you.
the turkey. Yeah, she has done nothing.
I will butcher it.
Ciao.
Bye bye,
Luigi.
everybody.
Bye.
Ciao.
Ciao.